Good morning everyone. So today we are going to discuss tutorial sheet 7, which is based on the chapter planar graphs. So the first problem says that which of the following graphs are planar. If they are planar, then the easiest way to show they are planar is that you must show the planar drawing, and to show non-planar you can use the Kuratowski theorem or the Menger's theorem. So first and third graphs are planar, their planar drawing is as follows, and the middle one is not planar, so you can see that it has a subgraph. If you delete the required edges, so these edges are deleted, which is clearly visible. So after deleting these edges, you can see that it has a subdivision of K33. Please do try by yourself. There are 6 vertices. If you try by yourself, these 6 vertices and other vertices are of degree 2, so therefore it forms a subdivision of K33, and therefore from Kuratowski theorem it is not planar. Every subgraph of a planar graph is planar, of course, because it does not have a subgraph which is homeomorphic to K33 or K5, and therefore it is planar. Every subgraph of non-planar graph is non-planar. It is not true. We can easily see K33, it has many subgraphs which are planar. There is no simple bipartite planar graph with minimum degree at least 4. So we need to prove or disprove it. So to prove it, we will go by contradiction, which means that let us assume that there exists simple bipartite planar graph with minimum degree at least 4. So minimum degree at least 4, it means that degree sum is greater than equal to 4n. But we know that for the planar bipartite graph, the number of the edges is less than equal to 2n minus 4, which means the degree sum is less than equal to 4n minus 8. So if we assume that there exists a simple bipartite graph with minimum degree at least 4, then we reach to a contradiction, because in that case the degree sum is greater than equal to 4n, but for planar bipartite graph the degree sum should be less than equal to 4n minus 8, and therefore the result is true. The next question says that determine all positive complete bipartite graphs which are planar. So if we consider K33, or if both the numbers are greater than equal to 3 simultaneously, then it would have a subgraph as K33, and therefore for sure it would be non-planar. It means the only choices are that one of the number should be less than 3. So K1, K2, and along with K1 you can take any positive integer, doesn't matter, it would remain planar. But if you go with K3 and s is greater than equal to 3, then it would for sure be non-planar. Let G be a planar graph with less than 12 vertices. Then we need to show that it has a vertex of degree at most 4. So we did the similar question in the class, which says that let G be a planar graph and then it has a vertex of degree at most 5. Now we put a restriction on the number of the vertices, and therefore the result has been changed. So again we'll try it by contradiction, which means let us assume that all the vertices, so the contradiction is that G has no vertex of degree at most 4, which means all the vertices have degree at least 5, and therefore the degree sum would be greater than equal to 5n. But for planarity we know that the number of the edges is less than equal to 3n minus 6, which means that degree sum is less than equal to 6n minus 12. Now it is given that n is less than equal to 11. So for n is less than equal to 11, you can easily verify that 5n is always greater than 6n minus 12. It means that it is given the graph is planar, but the degree sum is greater than 6n minus 12, which is a contradiction. So we start with a contradiction and end up with a contradiction, which proves the result that G has a vertex of degree at most 4. So let's move to the next question, which says that using Euler formula, show that if G is planar graph on n vertices and has a girth G. So recall that what is a girth? It is the size of the smallest cycle. Then G has at most G multiplied by n minus 2 by G minus 2 edges. Okay. So again recall that using Euler formula we have shown that for a planar graph the maximum number of the edges is 3n minus 6, and for a planar bipartite graph the maximum number of the edges is 2n minus 4. And to prove that in case of the 3n minus 6 we use the result that 3f is equal to 2e, and in the other case 4f is equal to 2e in case of the bipartite graph. Yes, if I recall the same result, then on the one side I can keep 2e, and I do not know the size of the faces, the face length, but I know that the smallest face length is G. So if I consider the smallest face length, here I know that the face length was 3. In the case of bipartite graph I knew that the face length was 4, but now I do not know. So if I consider the smallest face length, then the inequality comes and f remains as it is. This is the only relation we need to compute. After that rest is fine, because we know that the Euler formula, so n minus e plus f is equal to 2. If I substitute the values, then please do try it by yourself. The result comes out to be m is at most G multiplied by n minus 2 divided by G minus 2. Also, now based on this result we need to show that the Petersen graph is non-planar. It means if the number of edges are greater than G multiplied by n minus 2 by G minus 2, then the graph is non-planar. So for the Petersen graph, G is 5, m is 15 and n is 10. So 15, and on the other side G is 5 multiplied by 8, and minus 2 is 8 divided by 3, which is 13 point something. So clearly m is greater than G n minus 2 by G minus 2, and therefore the Petersen graph is non-planar, which we already know from the Kuratowski theorem. So this is one more result which is based on the Euler formula. So moving further, let's move to the next question, which says that prove that the complement of simple planar graph with at least 11 vertices is non-planar. It means that try any planar graph of order 11 or more than 11 and then try its complement, find its complement. You will easily observe that it always comes out to be non-planar. But why is it so? That we need to think. Now recall that for the planar graph, m is less than equal to 3n minus 6. Yes, if I consider the n is equal to 11, yes, then m is less than equal to 3.11 minus 6, which means m is less than equal to 27. Now if I consider a graph of order 11 whose number of the edges are at least 27 because it is planar, then its complement, so for its complement I have to think of K11 which has 55 edges. It means if this G is the graph, then G complement has at least 28 edges. So we have seen that if n is equal to 11, then m should be less than equal to 27 for planarity. It means if m is greater than 27, then it must be non-planar. So if I fix n is equal to 11, then its complement always have greater than 27 edges, and therefore it is always non-planar. Now if you think of the larger graph whose order is more than 11, then of course if it is a planar graph, it has a subgraph whose order is 11 and which is planar, and its complement comes out to be non-planar, which means that even for n greater than 11, the complement must have a subgraph which is non-planar, and that gives us a non-planar graph. You can also try to prove it using Euler formula or by contradiction. And then it says that also try to construct a self-complementary simple planar graph with 8 vertices. So if the order is greater than 10, then there cannot exist a self-complementary planar graph, because its complement would always be non-planar from this result. And this is why we are looking for a self-complementary graph with 8 vertices. So this is one of the graph. You can see it is planar, the order is 8, and this is the complement. So this is G, this is G complement. So you can see that it's a self-complementary graph. The next question is, we need to construct a 3 regular graph. Please do try these exercises by yourself. The answer may not be unique. Of diameter 3 with 12 vertices. So this is a very interesting example. It is not easy to construct, but you can observe by yourself that it is 3 regular. Its diameter is 3. From one vertex you can always reach to the other vertex with the maximum length, with a path of maximum length 3, and its order is 12. So this is the last question, and a very interesting question. It says that for any 3 vertices x, y, z of graph G, which is planar and its order is n, the sum of the degrees of d of x, d of y, and d of z can be at most 2n plus 2. So x, y, z belongs to G. So let's mark x, y, and z, and we are claiming that their degree can be at most 2n plus 2. So to compute the degree of x, y, z, we need to see their adjacency among themselves, but at the same time we need to see their adjacency with the other n minus 3 vertices. Now among themselves, if each one is adjacent to the other one, then the degree of x is 2, degree of y is 2, degree of z is 2. So it contributed to 6 among themselves. If each one of them are adjacent, because this could be the worst case that all of them are adjacent among themselves. So in that case, we can see that the contribution to the degree sum d of x plus d of y plus d of z is 6, because degree of x is 2, degree of y is 2, and degree of z is 2. Now next information is the graph is planar. So planar means that it should not have k33 as a subgraph. Now there are remaining n minus 3 vertices. Among n minus 3 vertices, there cannot be 3 vertices which should be adjacent to all x, y, z. So we cannot find 3 vertices which should be adjacent to x, y, z, because then there will be k33. It means there could be only 2 vertices, let's say u and v, which can be adjacent to x, y, z. This is the worst case. So in that case, you can see that the degree of u, or in that case we have to just see the degree of x, y, z. So x can be adjacent to uv, y can be adjacent to uv, and z can be adjacent to uv. So maximum 6 degree can be added to the degree sum of x, y, z. Now for the remaining n minus 3 vertices, they can be adjacent to at most 2 of x, y, z. They cannot be adjacent to all 3. Yes, it means that for the remaining, sorry, this is n minus 5 vertices, each one can be adjacent to any two of three, so which gives you the degree sum of x y z to be 2 times n minus 5. So degree sum of x y z is less than equal to 6 plus 2 n minus 5, which gives you 2n plus 2. So very interesting question. Please do try to understand again by yourself, or you can try to think of some other approach. That's all from today's class. Thank you.